In lesson 6, we're going to talk a little bit about some of our intersecting chord rules. So we're going to branch into slightly more advanced than just our central and inscribed type of angles. Explain what is wrong in the diagram below of triangle inscribed in a circle. And the problem is right here. If we are to have a right angle, AC should be a diameter. Now AC is just a chord because it doesn't go through the center. So the problem is, since AC is not a diameter, angle B cannot be a semicircle. Okay, so what we want to make sure is that we're understanding, although that's a right angle, we do want to verify that the what would be the hypotenuse of that triangle is actually the diameter. So in circles, angles and arcs can also be created by intersecting chords. So like I said, we're going to expand a little bit more on our rules here. Our first rule we want to talk about is in a circle, when two chords intersect, the angle formed is equal to half the sum of the intercepted arcs. So these are when we have angles that are not inscribed because the vertex is not on the circle, and they're not central because the vertex is not in the middle. At the middle. They're just kind of like floating around somewhere randomly in the circle. Okay, so the rule is, so it'll be x equals, or your angle equals, so actually we'll change it to angle, is equal to arc plus arc divided by 2. So basically it's the average of the arcs. Now it's the average of the arcs that it opens up to and the one behind it. So if you look at this picture on the left here, x opens up to the 190 and what's behind it is 70. So x is going to be equal to 190 plus 70 divided by 2. 190 plus 70 is 260, and 260 divided by 2 is 130. Same thing here. In the middle, it opens up to the 66, and what's behind it? 70. So x is equal to 66 plus 70 over 2. So x is going to be equal to 138 over 2, which is going to be, 136 over 2, which is going to be equal to 68 degrees. Now here, this setup's a little bit different, so that's why we were careful. The 72 opens up to the 99, and then behind it is the x. So 72 is equal to 99 plus x over 2. So when the x is one of our arcs, what we're going to do is put the angle over 1, and we'll cross multiply. So we get 99 plus x equals 144. We'll subtract the 99 on both sides, and x is going to be 45 degrees. So in that case, then our arc would be 45 degrees. So in exercise 2, Christine claims if two chords intersect and the measure of each angle formed is the same as the measure of the arc intercepted by the angle, then each angle must be a central angle. So wants to know, is she correct? And then explain our response and draw a diagram. So I'm actually going to start with the diagram piece. All right, so I'm going to draw a circle, and then I'll put a dot in there for my center. So basically what they're saying is, if you have like I'll just start like a couple chords here. So basically if you have a 60-degree arc, and then where your chords intersect is also 60 degrees, then Christine's saying that it has to be a central angle, which is true. Think about it. Right here, these are vertical, which would then make this have to be 60 because the arc it opens up to and the arc behind it, when you add them up, you got to average to get the angle. So the answer is yes, she is correct, because she is correct. Because if an angle inside of a circle is equal to its intercepted arc, all right, an intercepted arc is just like the one it opens up to, it must be a central angle. All right, so if you notice, I go back here, all those angles that we got were different than the arcs, all right, because it's the average of the two. So if you're going to get that arc and that angle are exactly the same, then it has to be a central angle that it works with. So another important concept that involves intersecting chords is the length of their partitions. When two chords intersect within a circle, they form similar triangles, which means their partitions are in proportion. So if you think back to earlier in the year, anytime we had similar triangles, a lot of times we end up setting a proportion. So we're just going to prove this really quick. So in the diagram below, we want to draw AC and BD. All right, so we're just going to take our pencil and we're going to connect AC and DB to make two similar triangles. So if we want to state a set of vertical angles, all right, we can call them by letters or we'll just put the numbers in there. So then explain why ACD, okay, and I'm going to do this in a different color here. So explain why ACD and DBA are congruent. And this is where we have to think in terms of circle terms. So both angle C and angle B, both of them are inscribed angles because they're on the circle. Now angle C is inscribed to arc AD, and B is also inscribed to arc AD. So the reason that they are congruent is because both are inscribed to the same arc. All right, so obviously inscribed means cut in half. So if they're both cut in half of the same arc, then obviously they have to be equal. Okay, so state another set of angles that would be congruent by the same reason from B. Well, that would be our other ones at A and D. All right, you can see A opens up to CB or is inscribed to CB. D is also inscribed to CB. So we have angle CAB and angle BDC. All right. But remember, when we're proving similar triangles, we only need angle. So we technically had enough after part A and part B. All right. So in exercise 3, we proved that when two triangles are similar by angle, that allows us to state that the sides are in proportion. Now, this proportion here, let me just bring up the other one, talks about how the pieces of the triangles go together. So if we were to cross multiply this, what would we get? Well, we'd have AE times BE is equal to CE times DE. Okay, so if you look, AE and BE are part of the one chord, and CE times DE are part of the other chord. Okay, so the rule says if two chords intersect within a circle, then the product of the partition segments of one chord is equal to the product of the partition segments of the other. Now, that's a little bit confusing in the way it's written. Here's what we normally say as a rule. We go part times part equals part times part. Okay, so those first two are parts of the same chord, and the second two are parts of the same chord. All right, so let's take a look a little bit here. So we have in exercise 4, determine the value of x for each of the circles below. So let's look at the chord that has the x in it. So part of the chord has an x, the other part has a 6. So we're going to be 6 times x. We're going to multiply those two pieces together. And then the other chord is 4 and 9. So 4 times 9. When we multiply that out, 6 times x is 6x, 4 times 9 is 36. We divide both sides by 6, and we get that x is going to be equal to 6. All right. Now, it's not always true that it works out that those are both the same. It just happened for this one. Okay. It does happen a fair amount, but is not automatic. So if we look here, we have this one chord is x times x, all right, because both pieces of that are x. Now, here's where we have to be careful. They gave us a 3 here, all right, and this part of the chord is obviously a 2, but we need this whole remaining part of the chord. Now, why did they give us the 3? They gave us the 3 to show that 3 plus 2 is 5, so our radius is 5. So we know that the distance from O to that side of the circle is 5. But what does it really make the other side of the chord? It makes it 8. So we have to do 2 times 8. So we're not just multiplying by that number they gave us. We have to multiply by everything that's on the other side of that chord. So x times x is x squared. 2 times 8 is 16. Square root both sides, and you get that x is 4. All right, it's not going to be plus or minus 4 because we know our circles can have negative lengths. So in exercise 4, this is pretty much the same exact thing where we have x times x, and then we have 3 is clearly one part. So that gives us, this 3 gives us another radius of 6. So we're going to be 6 out there. What is the whole length of this chord? Will be 9. So it'll be 3 times 9. X squared equals 27. We'll square root both sides. We'll put this in simplest radical form. So square root 9, square root 3. And we get each part of that chord is 3 square root 3. Okay? So our 2 rules that we learned about circles today were our arc plus arc divided by 2 gives us any angle inside the circle that doesn't qualify as central or inscribed. And then when we're solving for missing parts of our chords, it's going to be our part times part equals part times part rule.